Okay, so in this video, what we're going to be looking at is something called the 68, 95, 99.7% rule and Z-scores. And in a subsequent video, we're looking at some more work examples. This one I'll show a short one just to give you an idea of what it is. And a separate video, we'll actually go into some actual work examples. All right, so basically what it revolves around, you have to have a normal distribution. So it means it has to be symmetric, approximately symmetric, as indicated here, or has to have a nice bell-shaped curve around the mean. So the mean is in that point there. So what this is saying is from this point there, okay, so that's our mean, it's as straight as I can get. For one standard deviation on either side covers 68% of your data. That's what that says there. Covers 68%. Now, if I go, that's what this one's saying here. If I go plus the standard deviation and minus the standard deviation from that value, I'll give you an example in a moment. That means you cover 68% of your data. If you go 2 standard deviations on either side of your mean, that means you cover 95% of your data. So you can find 95% of your data within those 2 standard deviations. If you go 3 standard deviations, okay, that's accounting for 99.7% of your data. So that means that little bit there and that little bit there account for 0.15% each, okay? And there's a breakdown, which not quite this one. There's another one there, which I'll show you in a moment. Okay, so that accounts for that. That accounts for that. Just to give you a quick idea of what I'm actually talking about, say our mean is 50, could be for whatever, and our standard deviation is 5. So if that's our mean score of 50, and I say plus or minus, so these are test scores. So the test scores was 50% and standard deviation of 5. That would mean 68% of your scores are going to be between 55, because it's one standard deviation that way. So that's what this part means here. It's a standard deviation plus or minus, so the mean plus or minus that standard deviation. So that becomes 45. So in this case, 68% of the test, the people who sat the test, would have got either somewhere between 45 and 55. If we looked at 95%, that means we'd say 40 and 60. So 40 and 60, if we've got a bell-shaped curve, a normal distribution, between 40 and 60, you would have, of people sitting the test, would have got that percentage. Okay, and that's the sort of really basic what it means. This is true. The numbers are a little bit off, so I'm gonna, and they're being fixed along here. When I say along here, I do mean along there. So let's have a quick look at this strategy first. The key to solving problems involving this rule is to determine whether the values involve the 1, 2, or 3 standard deviations from the mean. So if the specified values lie between 1, 2, or 3 standard deviations from the mean, then use this rule directly. It can be all below, use these tail percentages, and I'll get what that means in a moment. And because the normal distribution is symmetric, 50% of the values lie above, so 50% that way and 50% that way, okay? And so so what it's saying here is, this is where so it's 68, so we say 34. We're not gonna get her at 34.1, okay? So it's 34 here. So what it's saying when we talked about this bit here, we're using the tail because sometimes you can get questions saying it's effectively above that 2 standard deviations. So I need to use the percentage from both of those. So it'd be 2.35 plus 0.15. Okay, that's sort of what we're talking about there. All right, sorry, I skimmed through that too quickly. I'm going to go to another page just to show you what I mean. This is the one this is a nice one. Okay, that's what I'm sort of talking about there. So if if I know that my test results are all above 1 standard deviation, then I account for that. So that's going to be 13.5 plus that. So I think that is 16%. So then I could say 16% of my students got whatever, and I could backtrack and work out how many students got that value. That's what we're talking about in that situation. Okay, let's go back to this for a moment. All right, so the Z-score, and so that's how that works. And the Z-score and this rule can work a little bit hand in hand. Okay, so the Z-score is what we call a standardized score. It indicates the position of a specific data in relation to the mean. Okay, this is the formula. You're going to need that to have that in your summary book somewhere. I can show you different places where we can do it. To calculate a Z-score for a data value, use that formula where X is the score. So that's if you got scored 70, you would put 70 in there. Okay. The mean, if the mean was 50, you'd put 50 in there. Standard deviation, that was 5, you'd put 5 and you'd calculate. So it'd be like 70 minus 50, so 20 divided by 5 would be 4, so your Z-score would be 4, okay? In this particular example. A positive Z-score indicates the data value lies above the mean. 0 means it's equal to the mean, and a negative means it lies below, okay? So in this example here, we're saying the mean is this, okay? And I've written it down, mean 1 standard deviation that way, 2 standard deviations that way, 3 that way, and conversely negative 1 standard deviation. That's another 2 standard deviations, that's 3, but in the negative direction. Okay, so all of these indicate that your score is below the mean. Score is above the mean. And that's sort of how we sort of need to start looking at how these sort of work here, okay? That's the sort of the basic idea. Let's go back to this as a quick example. The standard Z-score is useful in comparing data values from different data sets. So what it's looking at is saying, well, so these are your results from 2 exams. You got a 74 and a 63. The mean, so 74 with a mean of 60 and a standard deviation of 12. That's for your maths. So English, you got a result of 63, a mean of 50. The mean was 50 for the whole class and standard deviation 8. Now looking at it, you think, well, in terms of the class, yeah, I got 74 for maths. Of course, I went better. But what this does is the standardized compares it, so you can say, well, compared to the whole class or the whole cohort of students in year 12 or year 11 or wherever you're doing a test, what was my score? Okay, was it good compared to them or not so good? So 74 in itself is a good score, but relative to everybody else, when I do this summary here, what I find is I get a Z-score of 1.17, but for English, I get 1.625. And what that's saying is, in terms of where it is, it's saying 1.17 would be like here, 1.625, well, that's probably a bit out still. It'd be like down here, and the other one's there. So you've got, in terms of who you're comparing against the rest of the class, you're doing much better than everybody else here for your maths, so for your English, but for your maths, relative to everybody else, you didn't do as well. That's the idea of a Z-score. And basically, as you can see here, I put 74, 60, and a 12, and I get that value. And I do the same process here. So you could make a statement here saying a student performed better in English relative to her classmates because her Z-score for English is higher. I will go through some worked examples in a different video. Thank you.